All right, so now you're fully equipped to do what you want to do from Theorem 113. I think I'm going to give you some portion of it as homework, and I'm going to do one portion in lecture for this final video of the lecture. And you can see some other portions done in the notes, and maybe I'll select some other portions for possible presentations if you want to do those. Okay, so I'm choosing, let's see, so this, let me just say something about some of them. This one, associativity for addition, you already see kind of an induction step for it here, assuming you do induction on the right thing. So I'll leave you to read about that, but if you want to prove that this is true for all m, n, and k natural numbers, that you can always move the parentheses around, then the way to do that, most of these, the way to do is by induction, not all of them, but you need to pick what to do induction on, right? Are you doing induction, which variable, m, n, or k, are you going to do induction on? So you pick the right one, and you can see this looks kind of like an induction step, right? So a lot of the inductions, arguments by induction, need something to drive sort of the induction step. So like here, this one, proving commutativity for addition, that needs some kind of induction step, and you see it's done right before. So the idea when you're proving each of these is that they're put in a certain order so that when you're proving one, you can use all the previous ones. So you do this one first, you do this one before you do this one, because this one is serves as a good induction step that helps you do this one. Okay, one thing you might notice is this is here, and it's repeated from up here, right? It's just repeated. There's nothing new there. It's just the same one copied over. The reason it's copied over is just because it fits so nicely with all of these other ones. Like, it just ought to be here, right? 0 is a right identity for plus, 0 is a left identity for plus. Okay, what I want to do here is prove this one in the lecture. So you remember how easy this one was, right? This one was just a matter of applying the starting point in the recursive definition of add. That's all this was. But this one is going to be totally different, and it will require induction. This is theorem 113.3. So there's our setup, proof. Let n be a natural number. Then I want to prove that if I take 0 and I next it n times, then I get n. That's what I want to prove. Right, so we have kind of this asymmetric way of defining plus. Like when I say a plus b, I'm saying take a and then apply next to that b times. So 0 plus n is take 0 and apply next n times, unlike n plus 0, which is take n and then apply next 0 times. So these kind of different ideas there. Okay, so we're going to do this by induction, and actually, since we're doing it by induction, I've already made a mistake here. I shouldn't fix n, right? I shouldn't fix n and then just go ahead and try to prove this. I should do induction on n instead, do induction on the variable n. So we will prove by induction that for all n, if n is a natural number, then, and then here's my format for things to prove by induction, and what I'm going to prove is 0 plus n equals n. So my phi here, this is just scratch work. So what I'm secretly thinking, my phi is going to be 0 plus x equals x. That's what I'm trying to prove is true of all natural numbers x. And again, I'm just using x because it shows up here in my original statement of mathematical induction. So I need to prove a base case, the x equals 0 version, and I need to prove an induction step. So assume this, prove this. So let's do it. Okay, so here I'm starting to get things set up. So for my base case, I must prove that 0 plus 0 equals 0, right? Just put 0 in for n. And for the induction step, I'm about to talk about them in a sec. Let's just prove the base case first. So 0 plus 0 equals 0. So how might I do that? Well, I can go use the definition of add, right, and write this as add 0, 0, and then use the fact that add 0 is the identity function. But hang on, I actually would like to avoid using these things and instead, whenever I can, use this work that's already been done. So is there a way for me to use the work that's already been done? Yes, actually I can use this. In fact, it's legitimate to use this, which is the exact same thing, as well, because I'm on part 3 here, so I can always use the previous parts. But let me just go ahead and use this. So by theorem 112, part 2, applied to the case m equals 0, so we have this. We have this by theorem 112, part 2. So if the 0 shows up on the right, then things work. Here's 0 showing up on the right, so this 0 matches with that 0. Great. Of course, we cannot use theorem 112 part 2 for the overall thing we're proving, since for us the 0 shows up on the left. So that's it for the base case. Looks like I didn't need so much room. For the induction step, suppose n is a natural number, and suppose here we have our induction hypothesis. Assume that we have the induction hypothesis holding, so meaning that this actually holds for a specific n. Then we must prove, so if you use the original notation in the way we stated mathematical induction, we must prove that 0 plus next n equals next n. But I would say, actually, if you can avoid it, don't use the original notation. Now that we know next n is n plus 1, write n plus 1. Write n plus 1. This will be more helpful than you think. Like, there are actually a lot of times that I've written next n, and I've missed that I can use an earlier property that I've proven just because it was written sort of in this more obscure way rather than in this familiar way. So it will really help to write things in this way. Okay, so writing it as n plus 1, this is what we must prove. And definitely do not drop the parentheses when you do this kind of thing. So maybe later on, when you're proving things way beyond theorem 113, way later in the notes, or later in your life, go ahead and drop the parentheses, since this is all good and established, that it does not matter where you put the parentheses. But for now, if you're proving things in here, especially if you're proving this one, definitely keep the parentheses, just so that you can appreciate every time you move some parentheses around, appreciate that the work that was put into proving this is being used. All right, now do I want to move the parentheses around? Speaking of that, I think I do, because this is my induction hypothesis and I want to use it somehow, right? So you see, if I didn't write parentheses at all, then it wouldn't be clear that I need this, that I need the associativity. So it's just nice to have it be clear. So by 1, meaning by part 1 of this theorem, this is this. Now, by the induction hypothesis, by this thing here, 0 plus n is n, so I can replace the 0 plus n here by n. We then have I don't like this way of writing things. I find that it's hard to follow. How about I do this? chain of equalities like this. I find this to be easier to read. And then what I can do is just here say this is true by part 1 of the theorem we're trying to prove, the associativity of addition, and this is true by the induction hypothesis. And I think that's it. We proved what we needed. So we now know that if you apply next n times to 0, then you get n. In other words, we know 0 plus n is n. All right, so general advice whenever you're working on these, either on, if it's your homework or if you choose one of them for your presentation problem, general advice is a few pieces of advice. One is remember that you can always use the previous ones when you're working on any given one. 2 is remember to write next n as n plus 1 so that it becomes more clear to you what it is you're allowed to use. 3 is don't drop parentheses so that you can also make it more clear what's going on and acknowledge whenever you're using this. And 4 is if you're doing an induction, be clear about what variable you're doing induction on. So here in the one that I did as an example, that was not a problem. There was only one variable in sight to worry about. But for some of them, like for this one, there are 2 variables. So you need to be clear about which variable you're doing induction on and which variable is fixed throughout the proof. So make sure you use language that clarifies that. And finally, 5, if you're doing an induction and you find yourself stuck during the induction step, my suggestion is look at the induction hypothesis and ask yourself, how can I arrange things so that this becomes useful? How can I use this induction hypothesis? Let that guide what to do next.